All right. So welcome, everybody. It's a pleasure to welcome you to the kickstart of our distinguished seminar series, the CCMA seminar series of the Department of Civil and Environmental Engineering. I'm Professor Lydia Bouriba, and I'm organizer of this series founded in honor of Professor Cheng Mei for his seminal contributions in fluid mechanics and mechanics. And Professor Cheng Mei is with us today. Second row. The goal of the series is really to bring distinguished speakers in mechanics and fluids from around the world to discuss a bunch of topics at the front line relevant for CEE, but also MIT community and the Boston community. And the series wouldn't be possible without the CCMA fund and the support of the Department of Civil and Environmental Engineering. So I invite you also for the list of talks, today's talks, but all the history and future talks of the term to check the website, dss.mit.edu, that is behind me, where we have the compilations of the videos that you can use for teaching purposes and other educational research purposes. So today we are honored to host Professor Stéphane Zaleski. Professor Zaleski is professor at Sorbonne University in France, where he was head of the Jean Le Rond d'Alembert Institute from 2009 to 2018, one of the largest theoretical and applied mechanics laboratories in France. After his doctorate at École Normale Supérieure in Paris and early years at the physics laboratory at ENS, the École Normale Supérieure, he joined the mechanics group at Université Pierre and Marie Curie, which later became the Jean Le Rond d'Alembert Institute. So a lot of name changing, which I think used to be Paris 6. Is that? Yes. Yeah, all right. So Professor Zaleski pioneered and investigated a number of numerical methods for multi-phase flows with applications to atomization, cavitation, porous media flows, boiling, hydrometallurgy, contact lines and droplet impact, including several variants of the volume of fluid method, the diffuse interface method, and molecular dynamics. These include two-phase flows, including the SURFER and the Paris simulators as well. Professor Zaleski is on the editorial board of several journals and is associate editor of the Journal of Computational Physics and Computers. And he created with Patrick Huer a PhD and master's degree in fluid mechanics entirely in English. It's one of the only ones, I think, in France. Finally, Professor Zaleski is a fellow of the American Physical Society, and he received a number of prizes and recognitions, among them the Victor Nouri Prize of the Paris Academy of Sciences and the Silver Medal of CNRS. So without further ado, please join me in welcoming Professor Zaleski.
Well, thank you very much, Lydia. It's a great pleasure to be here, and especially to meet with Professor Cheng Mei again. We have known each other for a long time, and it's a pleasure to be here with you and with so many faces that I know from the several years since early times, maybe a long time ago, so long I will not say how long. So it's true that we have a lot of name changes. In fact, in France, it used to be said that when an institution was not working, France would create a new institution. So the university was not working, so already 200 years ago, the king created some schools, and then the schools and the university were not working, so the Republic created other schools, and then created CNRS and lots of other things. But now we have found a cheaper way. Instead of creating new institutions and letting the other ones plod along, so it means that you have to pay for n+1, n+2 institutions. Well, now we change their names. It's more efficient. And so, yes, Sorbonne University is a merger of two universities, and D'Alembert is the old mechanics in Paris. And so, this is the list of people who have helped me do the work in this talk. And here, Sagar is here. Raise your hand, Sagar. Yes, and so Sagar also helps me with that. And so why do we study atomization? And why do we study multi-phase fluid mechanics in general? So this is a rather classical problem. It's a problem of combustion. So you have a laser sheet here that illuminates a jet here in green coming out of this nozzle here. Then the combustion starts. So the blue region is where most of the reaction occurs. And the yellow region is the glow of the soot that is created by the chemical reaction. So of course, it's important to do this right and to reduce pollution from the soot with its health effects, and also possibly to have more efficient combustion. And in order to understand the soot formation and combustion, you need to know the size of these droplets, which is something you can measure, of course, but there is a great deal of unknowns about how these things are formed, so we would like to be able to predict it. This is another type of atomization that has motivated us. So here, it's not a conical jet, but a straight jet of liquid surrounded by gas. So this is a simpler device, but actually extremely efficient. It can generate a very high rate of droplet formation. This is yet another example. So if you are on the surface of the sea, one way to define the state of the sea is to define so-called Beaufort scale. So the Beaufort scale is a visual scale that tells you how rough the sea is. So if a Beaufort scale is 0, the sea is basically a mirror. And if the Beaufort scale is 12, well, there's some oceanographer here that will correct me, but if the Beaufort scale is 12, basically you sit here, you're not sure anymore whether you're above the water or below the water because there is so much spray and droplets. And so why is this interesting? Because in a rough sea, obviously you make a lot of droplets. So if the climate changes and while creating more and more storms, so maybe you will create more and more droplets and bubbles, and maybe these droplets and bubble will enhance the exchange between the ocean and atmosphere, so you have a feedback mechanism that could be interesting. So we want to study CO2 and temperature exchange between the ocean and atmosphere, so we need to understand these kind of things. And there are many other reasons to study that. And we have fantastic means to study that using numerical simulations. Perhaps this is among the most impressive progresses in fluid mechanics, the progress that simulations has allowed. In 2004, we had 5 million grid points, and we got these shapes which are essentially wrong. I mean, this is not the way the jet should look like. It's essentially the same jet done by Shinjo and Umemura on 5,000 cores, took 2 million CPU hours, has 6 billion grid points 6 years later. And 6 years later again, we had only 10 times more grid points this time, but it was done much more cheaply, maybe 3 orders of magnitude more cheaply. So with the Basilisk code. And so you see this mushroom shape is essentially the same here. And the resolution is, it seems similar. I mean, it's extremely expensive to improve the resolution of these things in terms of grid points. And so why would you do that? You know that Lando famously said that your motivations are only of interest to you and your mother. But I think it's still important, you know, to move forward in life, and in science, it's interesting to know, you know, why we're doing these things. So this is a picture of turbulence, and it's just a beautiful picture of turbulence. And so, you know, it's a complex phenomena with lots of objects interacting statistically. And there is a statistical theory for that, which is Kolmogorov's theory, which tells you that energy is injected here, dissipated here, and in between there is scaling. And if we understand the mechanism, there's a good chance we can predict the scaling. If I predicted scaling correctly, there's a good chance that we have understood the mechanics, or at least we haven't invalidated our understanding. So finding scaling in turbulence is really the fundamental issue here. And what about multi-phase turbulence? Can we do the same? Can we find some kind of scaling in multi-phase turbulence? No. That is the question. Can we find scaling in multi-phase turbulence? So at the end of the talk, we'll see whether we did find it or not. So how do we do it? Well, there are several steps. This is a set of methods that many people, including some who are here, have developed in various ways. And the first step is geometry, then Navier-Stokes equations, surface tension, and finally variable viscosity and density. So geometry, well, geometry is difficult, and especially because of surface tension, because surface tension basically moves the interfaces with the third derivative of the interface position. So if it's a third derivative, any kind of noise on the interface position will be amplified considerably. So you need extreme accuracy on the interface. One way to do that is to track the surface velocity. And another way is to rewrite the dynamics of the surface or the time-dependent geometry using a weak form PDE. And so this is more indirect than this, but this is very fruitful in terms of numerical methods. We use a specific method called volume of fluid, in which Cij is the volume of the fluid in a given cell. So it would be 1 here, 0 here. And we have cells in between where it is fractional. Then we reconstruct the interface, and the trick here is to reconstruct the interfaces in a discontinuous way. The discontinuity is very small, but it tremendously simplifies the calculations. So we sort of voluntarily degrade the solution in order to make it more efficient. And eventually, it also makes it more precise. So that is, so there are methods such as off-the-shelf methods, which are basically methods for solving the PDE of the volume of fluid. And then there are specific geometric methods which are used in all these codes that were developed in our lab in Paris. And I will describe them quickly. First, you do a reconstruction step. So you compute an interface normal, then you place the interface segment. This has 12 critical cases. There are, here are 6 of the critical cases. There are 6 other critical cases in another case. Very strangely, this way of cutting a cube is patented. So it seems like a purely mathematical idea, but it is patented. Fortunately, it was patented by IBM only, and IBM will defend its patent only in relation to medical scanning engines. So it doesn't pretend to patent the mathematical idea, but only its implementation in medical scanners. But we are just lucky. If it was another company which had patented it, we couldn't do volume of fluid anymore. I couldn't talk to you. That everything I was doing would be covered. So actually, with Dan Rothman, we received 30 years ago an email from Richard Stallman telling us to free our codes. And I was a bit slow to follow his advice, but eventually I had a fantastic student called Stéphane Popinet who told me that he wanted all his codes to be free. And then it continued like that. Actually, it's a recurring story. Maybe most of you don't know that, but the open form code is free because one of the students of Grossman told him he was fed up with Grossman making money out of his students, and he wanted the code to be free. I don't know. We can discuss that later about. And so, by the way, this is the only political slide in this talk. So, surface evolution. Well, we have to test these methods mathematically. So we put a vortex and a droplet in the vortex. And with zillions of particles, it gives us this reference solution. And then we compare it to volume of fluid. And we can use various methods. There is the method of Dick Ewer here, which would ensure to machine accuracy that the volume of each one of these droplets is conserved. If you see a picture like that, you can distinguish a volume of fluid calculation from other competing methods, such as level sets, because the level set method will evaporate this thin ligament here, or this thin sheet. But volume of fluid method will conserve volume, and so you will get these large blobs here. I will return to that later. Then we have to solve Navier-Stokes. There is nothing really original here in our approach. There are lots of Navier-Stokes methods around. And surface tension is more tricky. Surface tension is doubly difficult because you have a delta function here, and you have the curvature here. So let me spend some time on this. First of all, let me mention that if we do this wrong, then we'll get something called spurious currents. And the first time we saw spurious currents with Dan, and unfortunately, we found it was so wrong that we didn't publish it. But then the second time I saw them, I finally decided to publish them, but with another method. And finally, we understood where it came from. And so it comes from the fact that you cannot balance exactly the pressure gradient with this term unless you pay attention. And once you do that, you use the so-called balance force algorithm that ensures that the two discretization operator here, grad H, are equivalent. And you improve the computation of the curvature, and then you have to wait long enough. Actually, Popina in 2009 was the first to realize that you had to wait long enough, which seems trivial, but in fact, water has very low viscosity and very high surface tension. So as a result, the damping of capillary wave is very slow. And you can get spurious motion that is actually physical because it's the remnant capillary oscillations of the droplet. It's a remnant sort of natural vibration of the droplet you observe and not spurious currents. So how do we improve the curvature calculation? We compute these so-called height functions, and this is really the key to the accuracy of the method. And so then we take finite differences of the height function, and we get the curvature. Another difficulty is variable viscosity. So we can take arithmetic or harmonic mean. The harmonic mean, it turns out to be the exact, but this is still a tricky issue, and it's the best way to deal with viscosity has not yet been found. We have approximate solutions, but it's not completely right. We have variable density issues. There are many ways to deal with the variable density, the so-called momentum conserving methods, which actually consistent VOF method. That is, they advect the momentum near the interface using the same scheme used for the VOF corollary function. So you have this scheme that involves reconstruction and then various advection schemes, and you do exactly the same one to advect the momentum. So you reconstruct the interface, and then you can find from the interface reconstruction how much momentum to advect. You can use extrapolation methods. You can combine the methods with flux limiters. You can use filtering. And why do you need to spend so much time on this? It's because if you want to do something just as simple as a falling raindrop of 1.5 millimeter in radius, it's already very difficult. It requires at least 200 grid points per diameter. So I used to torture my students to give them as an assignment to compute a falling raindrop. And then Sagar knows that because he was tortured like the others. And I couldn't find it until eventually someone just broke his computer with 200 grid points in a droplet. Yeah, I'm evil. I make my students, I see some of you making faces, I make my students break their computers. So, a raindrop. A raindrop never looks like this. This is something that people got from Disney, okay? A small raindrop is spherical. A larger raindrop is like a kind of bun or pancake. An even larger raindrop starts showing some deformation, and eventually the largest raindrops break. And if you take a standard code, like Jerry's, to compute a raindrop, instead of these shapes, you get something completely wrong like this. And in fact, this comes from the fact that there is a mixing of the gas acceleration and the liquid density here. So the pressure gradient is multiplied by the density ratio. So for air water, you have a density ratio of about 3 orders of magnitude, 10 to the 3. So you have a pressure gradient which is 1,000 times larger than it should be in this region. So that's why you see these large pressures. And they have to be balanced by the capillary force, so that you get this large curvature here to balance the unphysical pressure. So this is very embarrassing. And eventually after that, the droplet breaks. Actually, in 3D, it's even worse. So you get this kind of thing, which is not atomization, that's just spurious numerics. This is really embarrassing. How, a question that people don't ask me frequently enough, how do you know what you are seeing is not just spurious numerics? The guys who did that were called Feng Xiao, Dennett, and Mark Gwerk. Which is fun because Feng Xiao, there are two guys called Feng Xiao. There's the student who did that, and there is a professor in Japan who is also an expert on the volume of fluid method. So I call him Young Feng Xiao. So what Young Feng Xiao did, he used extrapolation, which is a standard method to improve things. And we do something else. And so we look at this flow, and we plot the kinetic energy of the droplet. And when we get this burst, we know there is no physical way we can extract that much kinetic energy from the boundary conditions. So we know this is spurious. But it's kind of fun. Let me show you. So when the thing happens, we have this bump, blank. Okay, this is sort of fun, but this is wrong. We managed to improve these things, and with various improvements, we get this kind of flow. So that's a real raindrop at 8 millimeters. It's real because we have the real water viscosity, water surface tension, etc. And you see all this turbulence behind. So we're quite happy with that. We can also match the terminal velocity. We can match the oscillation frequency of the droplets, and everything is fine. We plot the kinetic energy. So we don't have these huge spikes, but we still have too much kinetic energy, too much agitation noise for 8 points per droplet. And then it decreases. Eventually here, around 32 points, it becomes more reasonable. And, well, it's still a bit agitated. And finally, there's essentially no difference between 64 and 128. The drift you see here comes from a controller that we add to Navier-Stokes to keep the droplet in the center of the box. So this is essentially solved around 64 points per droplet, which is still only a third of the 200 points we needed. So we still need even better methods to maybe have reasonable droplets with much less points. But even if the droplets are sort of noisy, they will more or less keep their shape and not atomize wrong. So we have a rough method, and we can move on to compute real flows. So this is a real flow. This is the Grenoble experiment. So you have from tranquilizers here a glass flow, a water flow, and then you see this atomization occurs here inside this, visualized by this laser sheet. There is the detail of A region shows a separator plate, which has a thickness of 150 microns. And the water is fed from this overflowing tank. So actually, the fact that the water comes from this tank and is recycled into this tank has some consequence on what happens later. So I will let you guess at the end of my talk what is the importance of this tank. But in the meantime, this is a sketch of the flow. So we have the separator plate here. We have this big Kelvin-Helmholtz bellows that extracts some liquid sheets out of here. And this is our grid. So the grid is a so-called octree or quadtree grid. So we have square cells which are subdivided until they are fine enough to cover the phenomena we want to study. We want to verify this method. So to verify this method, we need some experiments, but we also need some theory. So for the theory, we use the linear stability theory of small perturbations, the growth of small perturbations. And to understand the results of this theory, we need to understand about absolute and convective instabilities. So absolute instabilities are instability for which a small perturbation at the origin of space and time expands both forward and backward in space. It expands both upstream and downstream. When this happens in a cavity, you will have a well-defined oscillator frequency or a so-called global mode. On the other hand, if you have a convective instability, you will have an unstable region that only goes downstream. So any information that is here doesn't feed back on itself, and so the system is just a noise amplifier. That's the linear theory. Of course, nonlinearities can complexify it enormously, but we can still compare this to the experiment and the simulations. So in order to compare that, we need a velocity profile. So here the separator plate is the gas boundary layer, the liquid boundary layer, and there is a velocity defect, which is in fact a wake, that slowly relaxes to give finally something like a tench profile or two merged boundary layers without the velocity defect. The amount of velocity defect is an essential parameter. We can vary the profiles by varying this velocity defect. And for delta d equal to 1, there's no velocity defect. For delta d equal to 0.1, there is a full velocity defect. Okay, so this this has many parameters: Reynolds numbers, Weber's numbers, density ratios, viscosity ratios. But the most important parameter is this momentum ratio m. Why is this the most important parameter? Because this is basically the ratio of dynamic pressures, and it doesn't depend on viscosity or surface tension. On the large scale, at very large Reynolds numbers, you expect this to be the main parameter that describes what happens. And so for air and water, this was studied by the group of Grenoble. And here are three power spectra obtained for various values of m. So the power spectrum is the amount of energy in each wavelength or each frequency. And if you see a spike in the power spectrum, it means that you have a single frequency. So you have a well-defined oscillator, you have a clock. So that means you have an absolute instability. And if you have a broad spectrum like this, you have basically a noise amplifier. And if you look at this diagram, you'll see the predicted or measured frequencies. So the black dots are the experimentally measured frequencies, and the colored pluses and circles are the frequencies predicted by the linear theory, LT. And so you see that if you put the delta d equal 1, that is no wake, you predict the transition from absolute to convective here. Otherwise, you predict it here. And you see that the frequencies are well predicted using delta d equals 0.1 up to the absolute convective transition. And below here, you have a noise amplifier, so you cannot predict the frequency. It's a function of the noise that you put upstream. So this shows a good agreement between the experiment and the theory. But we can go further, and we can compare all three, numerics, experiments, and theory. So the theory is by Otto, Thomas Buck, and Maurice Rossi. And that's the result. So the experiments are here on the green line. The spatial linear theory with a wake flow is very close to the experiment. The spatial theory without wake flow is a bit further away. And the temporal theory, which is what you obtain if you suppose a periodic flow instead of a spatially developing flow, is completely wrong. The numerics are these black lines. This is a kind of rough power spectrum. The power spectrum of the numerics is much less rich than the power spectrum of the experiments, because basically in experiments you can run forever, you can run for thousands of periods, and in the numerics we run only for approximately 7 periods. And so for that reason we don't have precisely the peak, but it's not too far from the experiment. So that's really a very nice achievement, that we were able to fit finally the experiment, the theory. So it is a kind of verification of the method in a realistic setup. So we can have some confidence that the method works. There are other validations. For example, there is a direct comparison of the temporal growth rate, which can be made with the numeric, so that, and there are lots of other checks, of course, but this is the one that is the most critical. Now you want to go to see how things become three-dimensional. All this theory was only two-dimensional, so all this discussion was only two-dimensional. There are two mechanisms. One says that sheets will detach ligaments, and the ligaments break into droplets. That was the theory of Dombrowski and Johns. And another one says, another observation says that you get holes in the sheets. The holes expand. It's the expansion of the holes which eventually gives you the ligaments. So let's try to investigate that numerically, but we cannot investigate that, contrary to the previous case, with air and water conditions. It's either too expensive or too unsafe, because I've shown you about the large density ratios and the kinetic energy, which is still a bit spurious in the droplets. It's much more safe to do this with moderate density ratio. So we design a synthetic case with a more moderate density ratio. And we use a new volume of fluid code developed by Greater Tryggvason and myself and others. And this is the synthetic case. So basically the gas is at higher pressure. The gas is like at 50 bars. So we have a gas-liquid density ratio of 20. For the viscosity ratio is also of the order of 20. The surface tension is 1/20. So basically we call this the A20 case. And the injection velocity is also about 20. This is a kind of private joke, because the aerospace people have an A100 case, so we have the A20 case. So the flow looks like this. Again, you have the separator plate, the two streams, and we will see gas-gas mixing layer, gas-liquid mixing layers, and we see sheets that eventually atomize into droplets. So the sheets develop here, and they sort of curl like this and atomize into droplets. There's a lot of vorticity generated behind the sheets and also on top of the sheets. So these are the dimensionless numbers, okay, all equal to 20, almost all equal to 20. The Reynolds number, however, are relatively large. The Reynolds number based on the thickness of this layer is of order 8,000, which is about the maximum you can get. The Reynolds number based on the thickness of the boundary layer is of order 1,000. This is really the important Reynolds number. So this is what tells you have a large Reynolds number. And then one question we ask, can we make a valid simulation of that? And to have a valid simulation, you need grids that are fine enough. So will our grids be fine enough? So to figure this out, we took a sequence of 4 grids, M0 to M3. And each grid has a grid size divided by 2. So the final grid size is 3 microns. And so there are 256 points in the liquid sheet thickness, which should be sufficient to have a Reynolds number of 8,000. All in all, the M3 grid costs 20 million CPU hours. So that's also why I like to ask the question why, because why do you spend 20 million hours? I mean, it has to be something interesting, right? So we needed actually European grants of computer time to do that, thanks to Prace. And also French national grants. And what do we do with that? So we get this kind of flows. So these big red tubes, and this is the top gas-gas mixing layer. The blue vorticity comes from the gas-liquid mixing layer. And then the green vorticity is secondary vortices that sort of wrap around the primary vortices. You get all the characteristics of turbulence. You get hairpin vortices. You get a turbulent boundary layer. You get wave-vortex interaction. You get a turbulent wake behind the sheets. And so this looks very much like single-phase turbulence in these regions. If you remove the vorticity, you can see more specifically the interface. So you see these sheets forming and then atomizing. And so is this correct? So one of the things we want to see is there any convergence as we refine the grid? And so in this sketch, you can see the effect of a grid refinement on the tip of the sheets. The sheets are under-resolved. You see that they have these structures which look like a plastic sheet that has been torn away. But as you refine the grid, you start seeing the Taylor-Kulik rim. You get this. The Taylor-Kulik rim is this cylindrical structure at the end of the sheet. And finally, you get a rim which is not only well characterized, but it's also sort of corrugated or irregular in shape. And so this is precisely the kind of things you see in the experiment. So you really need the M3 grid to see something realistic. I want to zoom on the corrugated shapes. You get these kind of little holes at the end of the sheets. You see, when you see that in a simulation, you know it's wrong. You know, the sheets never break with these kind of holes. And moreover, this kind of thing generates a large amount of spurious vorticity. So you cannot converge characteristics of the turbulence, such as the entropy. You can also look in detail at the details of the formation of the sheet. So you have a peak of vorticity just above this ridge, and this sort of pulls away this sheet. So you get the sheet, the end rim, and you must have a sufficient number of grid points in this to be valid. You can look at the ligament formation now. So that's the critical moment of this mechanism when the sheets transform into ligaments. So here you see this structure I've shown you before. The color here is the velocity. And you see that this structure elongates, and then it merges with the top structure and makes this ligament. So that's one way the ligaments form through nonlinear interactions between corrugations in the end rim. Another way the ligament forms is by these holes that appear here expand rapidly. So they are surrounded by ligaments, and then eventually the ligaments separate, and you get droplets from the breakup of the ligaments. This is a zoom on one of the ligaments. So you get again this velocity landscape. So you can see that the ligament is stretched by this field, and all of these ligament dynamics result in these distributions. So these are the 4 distributions from M0 to M3. Before I compare these M0 and M3 distributions, I will first look here at the effect of sample size. So the sample size here fluctuates with the number of elements in the sample. So the blue and green lines are the largest number of elements. So you see there seems to be a reduction in the error as you increase the number of samples. And here I compare all the distributions. This comparison doesn't show you much. But this is a raw distribution in terms of number of droplets. The number of droplets has to be rescaled because we exclude the smallest and the largest droplet. These distributions are not spontaneously normalized. They have to be renormalized by a constant factor. So if you do that, you obtain distributions like this. These are plots in various coordinates. So these coordinates are what I call the log normal coordinates. these are coordinates where the log normal is a parabola. And so dp should be a parabola in log d. And so you see the log normal is here, and the gamma is here. The log normal fits much better than the gamma for the most refined grids. In fact, if you look in more detail, so this is the log normal. We fit with a variance, or a standard deviation rather, of 1.2 and an average of 2.2. So the average is dimensional, but standard deviation is dimensionless. If you have sigma smaller than 2, that means that you have less than a decade of scaling. So you don't have an enormous range of scaling. You can see whether this is converged by looking at the overlap between M3 and M2, so between the green and the red here. You have an overlap up to this noise over this whole blue region, and non-overlap here. It depends on the coordinates you're using. If you use linear coordinates, you clearly see the overlap. If you use log coordinates, you don't see the overlap. These vertical lines are the grid size. So you also extend the overlap by reducing the grid size. You basically have two uncertainties here. One at large radius, which I don't even show, which is statistical, and also the uncertainty is due to the fact that your experiment has a finite size. So it makes no sense to look at the distribution above a certain size. Basically, above the thickness of the layer, it makes no sense. So above maybe a half a millimeter, the distributions make no sense. And at small grid sizes, this makes no sense because you reach the grid size. Or if you are doing an experiment because you reach the resolution of your measurement device. The measurement device can be photographic or can be probes that are sensitive to being wet by a droplet, and this is also limited. So this is, these are experimental distributions, again, obtained by Sylvain Marty from the Grenoble group, and they also clearly see that, that the preferred distribution is log normal. The gamma here is this dotted line and is clearly very, very far away. There's a strong controversy about this because numerically I found log normal, but more importantly, the Grenoble group also found log normal. Emmanuel Villermo says that if you don't find gamma, that you made your experiment wrong. So this is a bit of controversial. I don't say anything. For my numerics, I'm not sure I have enough data, but for the experiments, it's a pity if you don't see these experiments in the literature. But well, for some reason, the Grenoble people didn't really publish that. So it is only in the Sylvain Marty thesis. So this is a little bit embarrassing. But back to numerics. If you have again this log normal plot, these are the data obtained by another numerical experiment by Marcus Hermann. And he has these three sets of data, the squares, the circles, and the triangles, and they converge to the log normal. How do they converge to the log normal? It's using the so-called G-grid, that he needs to refine his grid, having only for the level set, so the characterization of the interface. And when he does that, he progresses from this point to these points. In our case, the situation is a bit different. As we refine the grid, we go from the pink grid to the blue, to the green, to the red. So the refinement doesn't follow at all the same path. So I call this an excess number of droplets. Each coarse grid gives you too many droplets here, while the Hermann calculation gives you too few droplets. Why is that? Again, I'm showing here a fit of the parabolas in the log normal coordinates. So you see that you have too many of the green droplets over the red droplets. So how it is possible? Well, there is a different behavior of the volume of fluid and the level set simulations. So you remember this graph. I told you you can see that it's volume of fluid because you see these droplets because of the volume conservation of the volume of fluid. The level set, on the contrary, will eliminate this droplet by evaporating the tail of the ligament. And so if you break a sheet in volume of fluid, the sheet will break when it arrives at the grid size, and you will get these big droplets in addition, as you've seen on the test case. In the real case, you probably, the reality breaks at a much smaller scale than the numerics. You will get much smaller droplets. But in level set, you will see nothing. You will just eliminate most of these droplets by evaporation. So level set will have too few droplets, and volume of fluid will have somewhat too many big droplets. And let's see, how many grid points do we need? I have plotted here the number of the grid size you needed to overlap the distribution. So that's basically a convergence study. And you see that as you decrease the grid size, you decrease also the resolved droplet over this kind of straight line. And the conclusion is that basically you fit the distributions fit if you have approximately 20 grid points per droplet diameter. This is better than the 64 grid points I mentioned before, but this is because we have a lower density ratio, perhaps. Let me show you another case of atomization that's basically the end for the sheared layer. We study a different case where you put a light liquid here in a box. So this is also an experiment you could do. The light liquid will rise and atomize. So this is atomization in a box. The advantage is that you don't need to, you don't depend so much on initial condition on upstream turbulence. It's over when it has overturned, it's quickly done, and it's sort of shielded from external disturbances. And it was also very much used by people to test LES models of multi-phase flow. So the group of authors who do that did a lot of LES. And so, unfortunately, the Reynolds number is way too large. This is, the fondness of people for turbulence pushes them to use exaggerated Reynolds numbers. So it's no possible way that this can be ever converged. But it's sort of fun, okay? It gives you this big distribution of droplets. That's the time at which their entropy is maximum. And so you get these distributions, and if I plot them again in the log normal coordinates, you see nothing. You see absolutely, maybe something would happen here, but here you mostly see a Pareto distribution, 1 over R. This shows you that this is a completely different mechanism of atomization where this, and at a much, much larger scale. So we also analyzed the flapping frequency in the 3D experiment. So we again get 7 periods as before. And so we again fit the predicted frequency by the Otto, Rossi, and Bock linear theory. So 3D code also works. We look at I mentioned in the simulation the importance of holes and their expansion. Now I'm going to show you a real experiment where you see these are the waves that you see in the simulations that move back and forth. We move downstream. And I'm going to zoom on them. So the wave is somewhere here. In advance of the wave, there is a pocket of liquid which was engulfed by the airstream and is going to bulge like a bag atomization, what's called a bag atomization. So it forms a bag. Here, the hole forms here, and then it expands. And we see this whole expansion also in other experiments. This is an experiment by Siggy, Torotsen, and others of droplet impact. You see this whole growth. From the whole growth, we can guess the thickness of the sheet. It's 16 microns. In the Grenoble experiment, the thickness of the sheet deduced from whole growth is 64 microns. So why would a sheet break at 64 microns? You would say a sheet breaks when it reaches molecular length scale, when it reaches 100 nanometers, perhaps 10 nanometers. But no, it breaks much earlier. Why does it break much earlier? My guess is that these flows have impurities and bubbles. Lydia here has done fantastic experiments to explain bursting. But in the Grenoble experiment, you remember you had this reservoir, this tank. I think this tank is full of bubbles. And so the bubbles help break the sheets. But it's just a guess. The Grenoble people don't agree with me. So I don't know why you have such big sheets. So there are many questions which are still unanswered. And let me summarize these questions. One super important question for statistics, is the system ergodic? If you remember statistical mechanics or statistical physics 101, the essential thing is to suppose there is an equilibrium distribution that describes the statistics, the Gibbs distribution, and that the system is ergodic. If you do single-phase turbulence, if you're a very sophisticated single-phase turbulence person, you will redo an ensemble of experiments to make sure you have the statistics right. In multi-phase, it's very expensive, so we haven't yet started doing an ensemble of experiments, but we should do that to know whether the system is ergodic, whether we're just seeing a fluctuation. We need to know what's the statistical accuracy of the distribution. So we have shown you some attempts of finding that, but as long as we don't know whether it's ergodic or not, we cannot say that. We need to know what determines the range of scale observed. Is it, why is the variance of the log normal so small? Why is it only 1 or 2? And we also need to find out what's the effect of the density ratio. So for that, we have a recent paper. So for some reason, when I give talks, when I publish papers, they're illustrated, the editors decide to illustrate the experiments that I didn't do. As if you've seen the poster of this distinguished seminar, it's illustrated with a splash that has nothing to do with my work, but it's nice, I like it. And so this is a very nice work we did with Florence Marcotte, where we studied this. I mentioned bag atomization, so the wind will also blow a bag in the droplet, so this is a kind of the bag what you see. And we did it for variable Weber numbers and for variable density ratios. And you see the density ratio has a small effect. You don't see quite the same shapes, although they are similar. Basically, it expands more with the largest density ratios are here about 1,000, and here the smallest about 10. And so Florence did this nice graph of the full symbols as where you have fragmentation, large Weber, and the empty symbols are where you have no fragmentation. And you see it's not monotonous with density ratio. So there's a very mysterious effect of the density ratio here. So this could shed some light on whether our A20 simulations are just as in the real world, where you have rather 800 of density ratio. And so with this last look at droplets, I claim this is the end.